Okay, we're going to do everybody's favorite idea in calculus. It's related rates. You guys are going to love them by the end of this. Hi, Mr. Purvis. I'm the other calculus teacher. You haven't seen me yet, but let's get started, shall we? I'm going to post these notes for you, or Mr. Morris is going to post these notes for you, depending on who you have. But calculus is the study of change, right? We've been spending a lot of our time talking about derivatives so far. And derivatives are this like rate of change, this instantaneous rate of change at a point, slope at a point. You know the idea, right? So to study how things change, you've got to provide a context. We've been talking about taking derivatives, but we've been doing it with respect to a certain variable. For example, like the change of y with respect to x, right? That's dy dx. You can't just take a derivative. You have to take the derivative with respect to x or with respect to some other variable. So that took us to chain rule. And in chain rule, we talked about maybe taking the change of one function, but it was with respect to a different function. It wasn't necessarily x. So in the example of y is equal to u cubed and u is equal to sine x, well, to find dy dx, the rate of change of y with respect to x, you're going to take the derivative of y with respect to u and multiply by the derivative of u with respect to x. That will simplify to dy dx. But it's this context of taking a derivative with respect to a variable, right? X, u, q, t, it doesn't matter. We can take the derivative of anything with respect to any variable we so choose. In fact, with implicit differentiation, we took the derivative of things that weren't functions. We took the derivative of relations, things that were non-functions on the xy plane, and we were able to take the derivative of y with respect to x. You can take the derivative of p with respect to q. That would be dp dq. You can take the derivative of L with respect to B. It would be DL dB, right? dx dt, we would say that is the rate of change of x with respect to t. So this idea that derivatives are more than just slope, it's more than just the tangent line slope, right? Many relationships in the world are not just limited to the xy plane. Right? We're going to get away from the XY plane and we're going to talk about how we can use calculus in terms of real world quantities, right? Things that change, right? It just to limit calculus to XY plane. That's very constricting. Okay. So with related rates, we're going to see how mathematically linked quantities change with relation to time. Okay. So I'm going to explain a few things later about related rates. But it's this idea of seeing the world around us, seeing how things are changing, and having calculus and mathematics explain a lot of that change. Okay, so speaking of time, let's take a look at this clock. All right, I want you to think about this clock. Okay, now you might have a clock like this on your wrist or in your home somewhere, but the minute hand is spinning around, right? The hour hand kind of spins around with it. But if we could take a second to look at all of the different things that are changing, right? The angle in between, right? The theta, the angle in between the minute hand and the hour hand, the distance between the tips of those hour hands. So the distance here, K. We've got the distance H and the distance M. So think about what happens during the day as that minute hand spins around and that hour hand spins around. How is the distance between the two tips changing over time? Can you think? Sometimes it's getting smaller, sometimes it's getting bigger, right? But it's constantly changing. Go ahead, pause the video, go stare at a clock for a little while. No, don't do that, seriously. But like you can kind of imagine if you spun that around, that distance is going to be growing and shrinking. Okay, are there any quantities here that are constant? Well, okay, the hour hand length is staying constant. The minute hand length is staying constant. Okay, what's changing then? The angle between them, the distance between the tips, those are changing. Is there some mathematical relationship that you can that you can write, some equation, some formula that links together the length of h and the length of m and the distance k and the measure of angle theta. Whew, man, that one's going to be serious. But I bring this one up not only to talk about time, but also in something as simple as a clock. We can see the different moving pieces and how they're interrelated and how some change and some don't, and some are being affected by others. There's all these connected rates of change. So this idea of related rates is going to get really complicated for things like this, but it also is going to be some more simpler context. So I want to show you some simple things that we can kind of do when we attack a related rates problem. Okay, so to solve a related rates problem, first thing we want to do is make a sketch, right? Draw it on paper. You don't have to be like Leonardo da Vinci in order to draw these things. Any drawing will do. You don't have to make it elaborate. You just have to get a picture on paper. Okay, so label the drawing too. Make variables that are either given by the problem or variables that make sense. Right, so making a sketch. And then we want to list all the variables that are being used, including the units, right? So think about the things where the problem is saying increasing and decreasing and growing and shrinking. Like these words are all connected to rates of change. So look out for those. And you're always going to be asked to solve for a certain rate of change at a moment in time. Okay, so I'll kind of show you some things in there. So you're going to want to look out for you're solving for a certain rate, usually most of the time, and you're going to want to write all of those different pieces because there's going to be a lot of moving parts. We want to create that list of variables so we can have them handy. We know what we're looking for. All right, then we want to get a mathematical relationship that connects all of those variables. So it might be the Pythagorean theorem, or it might be the tangent of an angle is the opposite over the adjacent, or it might be some area, like the area of a circle or the area of a rectangle, or it could be a volume of a cone or a cylinder. There's a lot of different formulas that are locked up in here somewhere, and we're going to be accessing a lot of those formulas that you've seen in the past. So make sure that you can tie together all of those parts that are given in the problem with some mathematical relationship. Whew. Okay, we got 4 more steps. Okay, for variables that are constant, right, sub them in now. All right, so sometimes, like in the clock example, the length of the hour hand and the minute hand were constant. So we're going to sub those in. It's a lot easier to take derivatives of constants than it is variables, okay? Because the derivative of any constant is 0. So it's going to make the process a little bit simpler. All right, now we've come to the derivative part. So after we've made a sketch and listed variables and come up with an equation that links everything together and plugged in any constants, now and only now can we finally take the derivative. That's what we're all here to do. Take the derivative with respect to time. We're going to do that every single time with related rates problems, is take the derivative with respect to time. And think about this. You're going to be taking the derivative of x and y and p and q and a and b, all with respect to t. Right? Those variables don't match. So think about this as just a big implicit differentiation problem, right? Where you're taking the derivative, like when you took the derivative of y with respect to x, you always had to consider writing dy dx in that case. Or the derivative of x with respect to x, dx was just 1. So you're always going to end up with these extra little dy dt, dA dt, dB dt. Oh, you're going to end up with a lot of those little extra expressions in related rates problems. So don't be surprised if you get those. Okay, now after we've taken the derivative, we're going to sub in the remaining quantities. We're going to sub in the rates that are given in the problem, the lengths that are given in the problem, and then we're just going to solve for what we need to solve for. And at that point, we should be done. So the last step is to just take in the fact that you solved a related rates problem. Year after year, this is like the big, this is the doozy. This is the one that gets a lot of students confused. So if you've been confused already, well, you might like related rates because related rates is like applications of all of this derivative stuff that we've been doing. It's like we're bringing this into the real world. When you leave, next time you leave your house or look at your house or look at the things around you after watching this video, you're going to see things moving in connection with each other. And you're going to think, maybe I could explain this with calculus. And if you've done that, we've done our job. So when you solve related rates problems, give yourself a high five because daggone, these are tough problems and you will have done something if you get these done. All right, so let's talk about translating things into calculus. We've seen kind of a guideline, and it's a lot. I understand it's a lot, but we want to be able to take a problem and decipher the English words into mathematical expressions. So here's a couple of examples where we're just going to look simply at writing mathematical notation for English words. So in this 1A, if John is 5 feet tall and he's growing at 3 inches per year, all right, maybe we want to say that John's height is represented by h. So right now, h is 5, right? H is 5 feet. Now, growing, right? Growing. I kind of mentioned that earlier, right? That's a word that ties to rates of change. So growing at 3 inches a year. What is growing? Oh, his height is growing. So the rate of change of his height with respect to time would be dh dt. The change in height with respect to time, that is 3 inches per year. Okay, now the second one, a storm is 750 miles from shore and approaching at 200 miles a day. Okay, so maybe the distance of the storm, like right now, S is 750 miles. Now, the approaching, that sounds like a rate, doesn't it? Like that's telling me that it's changing. So we want to say that the rate of change of this distance is 200 miles a day. So let's think about that. So ds dt, the rate of change of the distance this mile that the storm is away from shore, is 200 miles a day. Now, hold the phone, right? Because what's happening? Is the distance growing or is the distance shrinking? Right? The word approaching means that it's getting closer. So is this distance, 750, getting bigger or is it getting smaller? It's getting smaller, isn't it? So that means ds dt is negative. Anytime something is getting smaller, the rate of change is negative. John's height was growing. It was getting bigger. So dh dt was positive 3 inches per year. Okay, so rates can be positive and negative. So keep that in mind. Let's do 2 more here. The radius of a puddle is 4 feet, and it's not changing. Well, we could say easily, okay, r is 4 feet, right? So if it's not changing, then the rate of change of the radius with respect to time is, what's that? What'd you say? 0. That's right. Yeah. If it's not changing, then the rate of change is 0. Not changing, it's not growing, not shrinking, is 0. Okay, the volume of a cone is 12 pi feet cubed. Okay, stop there. V is 12 pi cubic feet. All right, it's saying that it's shrinking, getting smaller at 5 pi inches cubed per minute. So that means the rate of change of volume with respect to time, the dv dt, is going to be negative, right? Negative because shrinking, getting smaller, getting little, and then the value 5 pi inches cubed per minute. You're going to see a theme here where we're given a value, but then we're told about a rate of change. growing, approaching, not changing, shrinking. We need to be able to turn that English words into into mathematical expression, mathematical equations, statements that involve calculus. Okay, so I'm going to show you your first related rates problem. Get ready. Here we go, baby. Let's go. Let's do it. All right. The radius of a circle is increasing at a rate of 3 centimeters per minute. Find the rate of change of the area when the radius is 6. Okay, so I've got the circle there. So what's happening? We got the length is a radius. Let's see. It says the radius of a circle is increasing. Okay, let's see. Okay, so we got R, right? R is one of the variables, right? The variables in my list here would be R. Let's see what else. Oh, A, the area of the circle. Let's see. So let's see if R changes. What's the rate of change of the radius? Wouldn't that be dr dt? If the radius changes, doesn't the area change as well? So that would be dA dt. We got a lot of things going on here. R and A. We're told that R is increasing at a rate of 3 centimeters per